I'd like to turn to something that will be more interesting and fun, and that is Professor Erik Brynjolfsson. So, as you know, Erik is the director for the Initiative on the Digital Economy. He's also the Schussel Family Professor of Management at the MIT Sloan School. He has many other accolades. I won't go through the long version of them, but for many years, before these particular themes of today or the last 4 years, he's been a leader for MIT and for the world in the way that information technology is changing organizational strategy, is changing productivity for workers, and is changing society. Erik has a bachelor's and master's degree from Harvard University and a PhD from MIT in managerial economics. Please welcome Erik Brynjolfsson.
Thank you, David, for that kind introduction. And this is really one of the most fun parts of my job. I get to talk to lots of smart people at MIT and work with the amazing team at the IDE. But it's really interesting to spend some time visiting companies and talking to alumni who are experiencing some of the things that we're researching and writing about. And as Dean Schmidtlein said, we're really looking forward to having this be interactive. We're genuinely interested in hearing about the challenges and the opportunities that you're all seeing. We have an all-star cast. You've seen the agenda of the amazing people that are going to be participating. But we're also going to be having Q&A and discussion as well. And so that will be a fun part of it as well. Today we're going to be talking a lot about how artificial intelligence is changing the economy and changing society, changing financial services. And frankly, there's been a lot of hype about it. There's a lot of excitement about it. And I think there's been some overclaiming about what artificial intelligence can do. And Hollywood kind of adds to that, both in a positive and a negative way about the capabilities. But it's also true that there are some really fundamental changes going on. There really is something at the core of this phenomenon. There's a reason why people are so excited, why billions of dollars are being invested by venture capital, tens of billions of dollars by bigger companies. Companies are reorienting themselves as being AI first. Whole countries are doing that as well. And today, one of the things we want to do is try to sort of separate that hype from the reality, give you a sense of what's really doable. And in particular, where we see our special role, understanding and translating how those technologies affect the economy, affect your businesses, change society. So not just the technical parts, but what it really is doing to change the economy. And that's something I don't think has been studied enough. There are a lot of people thinking about the technology, and they're making wondrous leaps in that. But the real bottleneck, the real shortage is in understanding how to translate that into value and actually, for that matter, prevent bad things from happening, because there are a lot of risks as well, and we'll talk about some of those today. Let me start by my talk this morning. We'll dive into some of this, what machine learning can do and what the implications are for the workforce. And let me start by first just defining some terms. So first we're going to be talking about artificial intelligence, which is this broad set of techniques. Does this work? Yes, it does. This broad set of techniques that try to imitate human intelligence. And this is actually an old field. It's been around for over 50 years. John McCarthy first coined the term back in the 1950s. After I graduated from college, I started an AI firm that built something called expert systems. I'm curious, how many people here have ever built expert systems or rule-based systems? Yeah, I see there's quite a few. So that was sort of the first wave, or one of the early waves of artificial intelligence. And that was based on the idea that we could reduce knowledge to a set of symbols, typically if-then rules. And if Socrates is a man and all men are mortal, we could make some inferences about whether Socrates was mortal or not, et cetera. And you could do this for diagnosing diseases. Sometimes hundreds or thousands of rules would be written up. And that was actually pretty powerful. It was able to do a number of things. And it spawned companies that we don't think of as AI companies, like SAP, that have massive rule bases and really billions, hundreds of billions of dollars worth of value. But it also had some very important limitations. And that is that these machines really did not learn. These were sort of what Andrew McAfee and I sometimes call the first wave of the second machine age. Yes, they were moving from augmenting muscles to augmenting brains. And so they were that second machine age of machines that can do thinking. But they were doing it only in very precise ways that we humans told them what to do. We had to codify the knowledge. Coding is codifying knowledge. And the limitation there is that we all know much more than we can tell. That's what Michael Polanyi said at one point, sometimes called Polanyi's paradox. And that limits what we can tell machines if we can't explain things. For instance, I know how to recognize my mother's face, but it'd be very hard for me to write a set of rules to codify that, or how to ride a bicycle. People who play the game of Go, which is in a way a simple game. There's only 2 kinds of pieces, and once you put a piece down, you can't even move it. Yet they don't even know how it is that they play the game, how they win. If you ask them, why did you make that move? They'll just say, if they're good, they'll just say, you know, it just felt like the right thing to do. I can't really explain what was going on in my brain. So that limits the kinds of things we can do with artificial intelligence. And that's where this new wave comes in, what we sometimes call the second wave, which is machines that learn. Machine learning works by having very large amounts of data, and then the machines figure out the patterns on their own, and they don't have to be explicitly programmed. And again, people have been tinkering around with this for decades, but it's really only in the past decade, and really the past few years, that it's taken off because of 3 important trends. First off, we just have a lot more data than we used to have. Digital data is available in orders of magnitude more than we have because of the internet, because of mobile telephony, because of instrumenting machinery and equipment, because of becoming Internet of Things. And this additional data makes it much easier to train machines. Secondly, we have far more computer power. The amount of computer power needed to train some of these systems would have taken literally centuries, or in one case, somebody estimated 250,000 years to train using 1990s vintage computers. But with modern computers, especially GPUs and some of the other technologies, we can crunch through that data much more effectively. And then last but not least, the third big change has been we've had significantly improved algorithms. So because of the first 2, people have been able to learn more quickly how to develop better machine learning algorithms. When you put those 3 things together, in many specific applications, there's been over 1,000,000-fold improvement in the performance of these systems. And I'll show you some data soon that we're crossing some very important thresholds, especially in the areas of perception and cognition. And part of the reason we're crossing those thresholds is because of a third concept that I want to share with you, which is this idea of deep learning. And that sounds deep, sounds like the kind of thing we do at MIT. It's also a technique in machine learning that uses neural nets with many, many layers, 8, 10, 12 or more layers of neural nets. And I'll even show you one in a little while so you get a sense of what's going on. But this particular paradigm has, again, been around for decades, but people have been able to use it much more effectively recently to make big progress in machine learning and therefore artificial intelligence and solve these new sets of questions. And that's the threshold that we're crossing now. That's very exciting for technologists. It's very exciting for economists and managers as well because it's opening up a whole new space of things that we could do that we couldn't do previously. So one example is in vision systems. Here's some data from a big database called ImageNet, and it has about 14 million images that humans have painstakingly labeled, but now machines are able to recognize them. And like the lower left there, those are oranges, or maybe they're lemons. I guess it depends a little bit on the shading. Machines are getting pretty good at recognizing them. Not perfect. But humans aren't perfect either. And if you look at the data, it's quite striking what's happened. Back in 2010, they only were about 70% accurate. And then that very steep part of the curve is when people started using deep learning techniques, neural network techniques to solve these problems. And suddenly they were able to do much, much better. And as you can see, recently they've crossed the threshold. Looking at similar data sets, the machines actually do better than humans. Now that's fun for technologists, but also if you're a manager, think about it. You are looking at 2 different ways of solving a problem. You have 2 potential inputs into your production function, like they teach you in Economics 101. So which one are you going to choose? Well, if one of them performs better and has a marginal cost approaching 0, you're going to start shifting the inputs over to that second technique, the one that has better performance and lower costs. And so that's something that we're beginning to see. We're still in the early stages of that, but crossing this threshold is really quite important. And this is a little bit about how they work. So here's very briefly, I think that if you're going to come to an MIT class, you have to see at least one bit of algebra there. So A neuron is really quite simple. All it is a weighted sum of these x's multiplied by the w's. And if that weighted sum is more than some threshold, like b, then the neuron fires. If not, it doesn't. So that's not real exciting. Seems very simple. What can you really do with that? And for a long time, people thought, well, there's not that much you can do with it. It's loosely modeled on human neurons, but by itself, it doesn't do much. Of course, it becomes interesting when you start putting lots and lots of them together in a network and having some kind of an algorithm like backpropagation that adjusts the weights so that it can learn from data. And you feed in data in that input layer, and it will, if the weights are right, it will, in the output layer, give you some kind of an answer. Here's some photographs, and the output layer might say cat or not cat. 0 or 1, is that a cat? Or is that the word yes? Or is that cancer? The magic happens in those middle layers, the hidden layers, which gradually develop on their own without us explicitly programming them, the understanding of concepts like this is an edge, this is a corner, this is an eye, and ultimately, this is a cat. So that's the essence of how they work. Of course, there's a lot more complexity there, but if you've got that, you sort of get the essence of what's going on there. These systems are not only good for images, but now there's a whole set of different things. And here's an article that Andy and I wrote in Harvard Business Review last year that describes some of the many applications. They all have this characteristic that you have a set of inputs X and a set of outputs Y, and you map between the two of them. You can do it with photographs and captions, like I was showing you earlier, but you can also do it with bits of voice, or you could do it with purchase histories, recipes. There's all sorts of things that you can put in the X's and the Y's, and the machine will learn what the relationship is on their own. So that's the essence of it. And so it doesn't work for all kinds of problems. It's not a universal artificial general intelligence. But if you can have a problem that fits in one of these kinds of characteristics, you can actually use machine learning quite effectively. So some of the applications that come to mind include vision and language, interacting with the physical world, problem solving. Let me give you some more specific examples. You can use it not just to recognize faces. If you've gone to Facebook, you've probably noticed that it starts captioning your friends' faces if you want them to. But you could also have it show it lots of examples of medical images, pathology slides or radiology slides, and it can say, okay, these ones ended up having cancer, these ones didn't end up having cancer. Is there some pattern? Is there some relationship between the two of them? And people have done this, and now there are a lot of papers being published in places like Nature and Science by machine learning experts that have shown that these systems can perform as well or better than human radiologists, human dermatologists, human pathologists at assessing whether there's a disease in that particular slide. Sometimes they even identify new characteristics that the humans hadn't been aware were markers for disease. You can use it to recognize real estate. There's lots of business applications. A team I'm working with at MIT is showing it images of houses and property, and it can estimate what is the value of that. If you also have data on the value, what is the appreciation likely to be? And again, it's outperforming humans in making predictions like that. And you can apply that, scale it up very easily to whole neighborhoods, to whole cities, and start making predictions. Combine it with other data and make even better predictions. And some of those require very sophisticated experts, but you can even use it for very simple problems. There's a great example that we talk about of just classifying different kinds of cucumbers. In Japan, apparently, they're very fussy about the different types of cucumbers, the color, the shape, et cetera. And there was a farmer there who, after harvesting the cucumbers, his poor mother had to sort them all into, I think it was a dozen or more different grades of cucumber each day, very time-consuming. Well, he trained a machine learning system. And what's interesting is this was not a machine learning expert who had a PhD in this. This was an ordinary guy who took a few online courses, and he used online software called TensorFlow, which is available for the grand price of $0.00. You can use it for free, and trained the system by exactly the example I showed you. Here's examples of category 1, category 2, category 3, et cetera, and the system learned on its own what the patterns were in a matter of a few weeks. So that gives you a sense of how even relatively small data sets with relatively little training can sometimes do practical, useful work. If you have some kind of unique data that Google or someone else doesn't have, you can build one of your own systems that may be doing something useful. And of course, speech recognition is another category that's a really important threshold. Again, a project I'm working on called the AI Index has documented how it's roughly matching, not quite as far ahead as vision systems, but roughly matching human performance. And again, I think that's a really important threshold in human history. I mean, if you look back, going from not being able to talk to our machines to being able to talk to our machines and reasonably expecting the machines to understand, carry out our instructions, even talk to us back. That's an important milestone, and we're just, in this room, we are among the generation that is experiencing that milestone. Again, the job and work implications are staggering. Another big category is interacting with the physical world. We all have heard about the self-driving cars. Here's one out of MIT, a startup called Nutonomy that is driving around in places like Singapore. But not all of the mobility is on wheels. Some of the more scary things that you walk around at MIT these days, you see creatures like this one from Jangbai Kim. I was at the track and field house, and this guy was running laps around it. And to make it more interesting, they were throwing objects in front of it. They were throwing like chairs and stools in front of it, and it would jump over them and keep going. Goes about 28 miles per hour, so do not try to outrun him. It's not going to work. And of course, in the factory, more and more machines. Another MIT alumnus, Rod Brooks, has a company called Rethink Robotics that's building robots like this. This is Baxter. And Baxter costs about $20,000, $25,000, can work 7 days a week, 24 hours a day. And for simple tasks like taking things off an assembly line, putting them in boxes, it can be trained very easily. There's no coding required. It learns on its own. If you show it, if you kind of guide its arm, it will figure out what it is you want it to do. And according to Rod Brooks' calculations, it's less than $4 an hour for those kinds of tasks. And there are lots of people all around the world that do those kinds of jobs in places in the United States, but of course in places in the developing world. I was just in China, and I saw a factory like this with thousands of people working in close quarters, and more of them are doing jobs that could soon be done by robots and are in fact being automated. But it's not just manual work. Those of you here in New York and in the financial services should be aware that there are lots of other kinds of problems that can also be solved, a lot of cognitive kinds of tasks. I was talking to folks at JP Morgan, and they described this system to me in some detail, a system that is learning to parse financial deals and figure out exactly what to do with those. And it said their staff took 360,000 hours. And now it's done in a few seconds by sorting through those. So that's another big change there. And these systems that are learning, I'll just show you a short little video that's kind of fun of how they can learn. And this is an example from a company called DeepMind. Google DeepMind is, I think, one of the reasons that Google bought them for about $600 million. What they did was they taught it how to play Atari video games, which doesn't sound all that exciting, but I want to tell you how they taught it. They didn't give it any of the rules or explain what the game was. They just gave it the raw pixels, ... And they said, here's a controller. You can kind of move it left and right, fiddle around. And here's a score. They gave it those 3 bits of information. And they said, now you figure it out. You figure out how to play the game, what the rules are, how to maximize your score. And they used a technique called reinforcement learning, a close cousin to the supervised learning systems I described before. And we can roll the video. You can see how it learned. At first, it really wasn't very good. It sort of randomly moved the paddle around, and sometimes got lucky, and sometimes it didn't. But the reinforcement learning system taught it that when it did something right, it got some points, and it would do more of whatever it was that got it the points. And so soon, after about 300 games, it was doing pretty well. It was like better than me anyways. So it was most of the time hitting the ball and doing fine. They let it keep running, and then it kept learning. And after 500 games, it kind of did something they didn't expect. It figured out this new strategy, which is you send the ball around behind the back, And that way, you get even more points, even faster. So it had stumbled across that, and it decided, hey, that's a really good thing to do. Let me do that more often. So that's an example of a machine learning system that can figure things out on its own. It worked not only for that particular game, Breakout, but it also worked for a dozen other video games using the same basic approach. They just showed it the raw pixels. Now, you should also know that there are another dozen and a half games that they tried to teach it and it couldn't figure it out. They were too complicated. And the main difference between the ones that it could figure out and the ones it couldn't was how quick that feedback loop was. In Breakout, what I just showed you a minute ago, they very quickly gave it the points when it did something correct. In other games like Pac-Man, you sometimes have to go up and to the left, even if you, because it's a maze, you eventually want to go down to the right. So you have to kind of do something a little counterintuitive to figure out how to win the game. In some of those more complicated games, it wasn't as good at thinking ahead and planning. So there's certainly areas where it works better. But one of the interesting things is you can take this and you can apply it to things like energy centers, data centers, I should say, and cutting the energy bills at the data centers. So the team applied similar reinforcement learning techniques there, and they thought of the data center as kind of a giant video game. The score is what is your electricity consumption, and the rules are how the things are connected to each other and what that does to the voltages and the amperages. And your controller is setting all the dials to adjust where the cooling goes, how high the air conditioning is, and so forth. And by fiddling around with those controls, it figured out a way to significantly improve the data center to the point where it cut the cooling by about 15% overall. So a significant improvement. And when you think about that, that's good not just in a data center, but it could be applied to any data center. It could be applied to any continuous processing system. It could be applied to a lot of financial services as well, where we have the system learning and figuring out what to do next. So let me now talk a little bit about how this might affect the workforce. And I want to stress again, we're very far from artificial general intelligence, this idea the machines can just do everything that humans can do. And therefore, I think that we're not in danger of seeing the end of work. There are many things that only humans can do. In fact, I would go further and say that there's an enormous amount of work in our society today that only people can do, and the real problem is redeploying people into those areas. But there are also a number of applications where machine learning does work very well, and it's especially true in these supervised learning categories. So what we undertook in a project with Tom Mitchell of Carnegie Mellon University, Daniel Rock, a PhD student at MIT, and some others, was to try to be very systematic and figure out which kinds of problems could be solved by machine learning and not be solved by machine learning, and what tasks would be affected. And the broad story was that these systems were making the economic pie bigger, creating a lot of wealth, but that there were a lot of people who weren't going to be positively affected. There were a lot of tasks that weren't being positively affected. And that can help explain why it is that median income is stagnating, why a lot of people today are being left behind, even as we have these wondrous advances in technology. So the way we went about doing it was we created a rubric, sort of a questionnaire of 23 questions. And the rubric guided what the right answers were. And if you applied this questionnaire to a particular task, it will tell you whether or not that task is suitable for machine learning. Is it something, not necessarily that's being done today by machine learning, but that could, in principle, be done by machine learning? And once we developed this rubric, we went around, we talked to lots of other experts in the field, and we kind of got a consensus around what the right set of questions were. We applied it to a giant database called ONET. This ONET has about 964 occupations in the economy. This is something the US government has divided the whole economy into occupations like professor, bus driver, radiologist. And for each of those occupations, it describes some of the work activities as well as some of the occupation-specific tasks that you have to do. What exactly is it that a bus driver does? What exactly is it that a radiologist does? For most of them, it had about 20 to 30 distinct tasks that needed to be done. So altogether, we had, as you can see there, about 18,000 tasks that we needed to classify. That is very time consuming. We did some of it ourselves. I did a bunch of them, which was kind of fun for the first dozen or so. My students did a bunch. And then we went to Crowdflower to kind of scale it up. It's a big platform like Mechanical Turk. And we gave them guidelines on how to answer those questions. So we had them all answered that way. And ultimately, we were able thereby to, for every task in the economy, get a score as to how suitable it was for machine learning. And it's important, and this is something Michael Chewy and I will talk about a little bit later in the panel, to think about these things more at the task level rather than at the occupation level. Because most occupations have a number of tasks that may be suitable for machine learning and others that aren't going to be suitable for machine learning. So it makes more sense to think about it a little bit more fine-grained than a whole job. So here's an example. Radiologists. I was just showing you a bunch of examples of machines recognizing medical images. And a lot of people see this as being kind of one of the jobs that's in the bullseye. And it turns out there are 27 distinct tasks listed in ONET for what a radiologist does. One of those tasks, task number 4, is interpret images using computer-aided detection or diagnosis systems. So that's what these machine learning systems are really quite good at doing. But look at all the other things they're doing as well. Number 5 is develop treatment plans for radiology patients, administer sedation. And number 2, I can hardly even pronounce it, perform interventional procedures such as image-guided biopsy, percutaneous transluminal angioplasty. I will stop there. But many of these, the point is that many of these other tasks actually are not that suitable for machine learning. And of the 27 tasks, only a handful of them were very suitable. Now, there are very important ones, maybe the core ones. You don't want to put equal weight on all of these different tasks. But this underscores this idea that even radiologists, many people say they'll go away. I think a more accurate thing is that their job's going to change quite a bit. Those tasks that are unaffected by machine learning will continue to be important for radiologists, but some components they will now increasingly delegate to machines. And work that we're doing with Erik Duhane, another PhD student, shows that sometimes, even for that category, combining a human and a machine can do better than the machine alone. They make different kinds of errors, and so when you combine them together, you can sometimes improve the performance than if you look at only one or the other. And it's not just radiologists. You could look at say, truck drivers, another iconic example many people talk about. Obviously, one of the things they do is drive trucks, number 1. But you can see they do lots of other things like wrap and secure goods using pads, packing paper, containers, or straps. We are very, very, very far from having robots that can do that. So while a machine may be increasingly able to do task number 1, we know venture capitalists who have companies that will be releasing self-driving trucks that do task number 1. Task number 2 and many of the other tasks will remain for humans to do. And so there'll be a rethinking, reorganization of the work rather than a complete replacement of the work. And I could go through many other occupations, but rather than that, I'll show you just quickly. Anybody in here who have a job of massage therapist? Okay, you guys are in good shape, not too many in this room. Concierge, any concierges? Okay, those are the people at the top of the list who are not in very good shape, that are likely to be very affected by machine learning. But you can roll these tasks up to the occupation level, and you get a sense of which ones have more of their tasks that are likely to be affected and less of them affected. I looked up economist and professor. They were sort of actually in the middle of the pack there. So that was interesting to see. What's striking, actually, and a little surprising to me, was if you kind of take all the occupations and you rank them from 0 to 100 in terms of their wages, 0 being the ones with the lowest wages, 100 with the ones at the highest percentile wages. And then on the vertical axis is how suitable are they for machine learning. You see kind of a broad scatter plot. It's not the case that, say, low-end jobs or middle jobs are more likely. It's actually, there's examples in all the different categories. There are some high-end jobs like radiologists that are significantly affected, some middle jobs, and some lower-end jobs like concierge and truck drivers. So unlike some of the other waves of automation, this one is not a simple extrapolation where it's just more of the same. We're going to see a very different set of people being affected, and I think a different set of effects on the labor force and outcomes. Let me just show you a couple of other fun things you can do with this data. It turns out that jobs are not evenly distributed in the United States. Some regions have a lot more of the kinds of jobs that are likely to be affected by machine learning The redder areas in particular, the bluer areas have relatively fewer jobs that are being affected by machine learning. You can subdivide it into lots of categories. If you look at only image data, we're not sure how fast these different kinds of machine learning will progress. Images was one of the areas that seems to be happening very fast. In this, it's a little different. Now the red areas are much broader. Those are the ones that use a lot of image data, or I should say, to be more precise, could be replaced by image recognition software. You can also look at text. You can look at speech. So you can slice it lots of different ways and get a sense of which parts of the country, which parts of the economy. You can do it by occupation. You can do it by industry. You can do it by company. And you start seeing where these waves are going to roll through over, we think, the next 5 to 10 years or so. Well, let me just sum up by saying that I think that this is a really fundamental transformation that's happening in the economy. We've had amazing breakthroughs in the core technologies. All indications are that these trends will only accelerate. If you go to some of the big conferences like AAAI I was at recently, or ICLR, where I'm keynoting next week, next Monday, you see that the attendance has just grown exponentially. I mean, doubling and redoubling over the past 4 or 5 years. So there's just a lot more brain power working on these problems. Add that to the other 3 trends of more data, more computational power, and better algorithms, and you have to be optimistic about what's happening with the core technologies. I'm not as optimistic about what's happening to updating our skills, updating our organizations, our institutions, our politics. Those are lagging, and this change, like earlier changes like electricity, the dynamo, internal combustion engine, will have fundamental effects on the economy. However, it's happening a lot faster this time, and we're just not making the adjustments rapidly enough. And a big goal of the Initiative on the Digital Economy is try to learn more quickly how we can adapt, who's going to be affected, and what we need to do. We don't think business as usual is going to solve the problem. We want to work more aggressively to find ways to create prosperity for the many and not just the few. So I'm hoping you guys will all join us in that mission to address that. We're going to hear some more now. I want to call up the panelists, but I want to thank you for giving me a chance to share some of this research, and in a minute we'll have the panel and we'll have some Q&A around that. Thank you.